So, the scientific method. Biology is a science, and as a science, it is dependent upon the scientific method in order to learn things, or at least mostly dependent on the scientific method. So, science is derived from the Latin verb meaning to know. And so, science is a way of knowing that is based off of inquiry, observation, things like that. Science developed from our capacity to be curious about the world around us, to look at things and ask how, why, what, and to then go out and look for answers to these questions. There's two main approaches to science. What's called discovery-based science and hypothesis-driven science. With discovery-based science, you mostly go out and describe things that you see. And you look for trends. All right? You observe enough about the world, you see this thing happen so many times that that it becomes obvious that there's a trend here which you describe. But when Jane Goodall went to study apes in Africa, she basically just interacted with them and described what it was that she saw. You know, this is how they behaved. This is how, they interacted with one another. This was their response when X happened. But she didn't try to intervene at all. She didn't set up an experiment. Now, it's not necessarily like good or bad. I'm not saying one of these methods is better than the other, although there are certainly circumstances where one of them is more appropriate than the other. But generally speaking, discovery science just finds out about whatever it is that you're observing, whereas hypothesis-driven science is more about questions and answers, and less about describing nature than explaining nature. Usually discovery science can't really tell you why something happens the way it does, whereas hypothesis-driven science is all about trying to discover the why. In this class, we're going to mostly be talking about hypothesis-driven science. But we will occasionally talk about discovery science as well. So I know all of you, probably since grade school, have had the scientific method drilled into your head, and you probably have had to memorize the steps of the scientific method at some point. But I think one of the things that tends to get lost is that the scientific method isn't just about finding things out about science. It's about finding out things about the world that we live in. And the scientific method can be used to discover things about anything that you can test. Whether it's about drugs or about pure science context, or just about why doesn't my car start, right? Hypothesis-driven science is based around this idea of a hypothesis, which is a tentative answer to a question, right? You ask a question, and then you come up with a reasonable answer for it. But just because we have an answer that sounds reasonable, we don't necessarily go, all right, that seems good, we're going to call it a day. I mean, people did that for thousands of years, and, it didn't work out all that great. So, people said, why do people get sick? I don't know. Maybe God's mad at them, right? And people just went, yeah, okay, that seems reasonable. I just went with that for years. But it turns out that wasn't correct. You go and test it, You don't find that, like, people who do things that you think might make God mad get sick more often. People get sick for reasons that seem to be unrelated to that. And so, when that hypothesis was put to the test, it was generally found to be lacking. We don't usually think in these terms, but you can use a hypothesis-driven science method to find the solutions to any problem that has to do with the world around us. Like, for instance, finding out why a TV remote fails. Once you have a hypothesis, you can use logic and, more importantly, experimentation to test it. A hypothesis, so this is an important thing about hypotheses. They have to be testable. A hypothesis that you can't test isn't useful, at least from a scientific perspective. Generally, the logic goes in sort of an if-then format. If my hypothesis is correct, then when I do this, that will happen. And then you do this and see if that happens. And if that doesn't happen, then your hypothesis has been falsified. Something about your hypothesis was wrong. And you have to go back and change your hypothesis and then test it again. Let's take a look at this in practice. So, you always start usually with an observation about the world, right? All scientific methodology starts with an observation. So let's take a problem here. You sit down, you want to watch, something on TV, and you pick up the remote, click, click, click. The remote isn't working. That's weird. That's your observation. The remote isn't working. Then you have a question. Why isn't the remote working? Right? That seems an obvious question. Most questions are obvious questions based off of the observation. They're often going to start with, like, why, what, or how. So, why isn't the remote working? What's wrong with the remote? Both great questions. In order to figure it out, you have to construct a hypothesis. Why do I think that, the remote isn't working? And your hypothesis should be reasonable. Because there are like an infinite amount of bad explanations, but there's only a limited number of good explanations. So your hypothesis for why the remote isn't working probably shouldn't be it's Tuesday, right? Because, it's Tuesday doesn't have anything to do with the remote. It probably shouldn't be something fantastical. If you're asking a question and you want to get it answered this way, then, you kind of have to assume that there is a reasonable explanation for why, and it should be something that is testable. So your hypothesis shouldn't be God told the remote not to work because you have no way of testing that. Right? So a reasonable hypothesis might be the batteries are dead. Okay. That seems to be pretty normal. Yeah, the batteries are dead. That could entirely be an issue, right? So you then make a prediction, right? You say, okay, this is our proposed experiment. If my hypothesis that the batteries are dead is correct, then when I replace the batteries, the remote should start working again. So that's our prediction with our experiment. So we now do the experiment, get some new batteries, you put them in the remote, and then see whether or not the remote works. And what can happen is Either your experiment supports the hypothesis, TV turns on, and you can now use that same prediction to make more predictions and test. Like at this point, you're probably going to go, all right, remote's working, TV time. But like you could say, all right, well, that being the case, what's another prediction I could make based off of this would be that like if I take these batteries and plug them into a different device, that device won't work because these are dead batteries. Now, in reality, you're probably just going to toss the batteries in the recycle bin and get on with watching your thing because you solved your problem. And that's what science lets you do. It lets you solve your problems. But some problems are more complex than others. The other possibility is that your experiment does not support the hypothesis. We would say that it disproves the hypothesis. So you put new batteries in, and the remotes still don't work. Okay, what does that mean? That means that your hypothesis was incorrect. At least in some way. Your hypothesis might be partially correct. Like for instance, maybe the batteries were dead and the remote was broken, right? In which case your hypothesis might be partially right, but it's not complete. That's a possibility. You may need to do more than one thing. It's also possible that your experiment was flawed, all right? With something as simple as replacing batteries, this is unlikely to be the case. But sometimes you have very complicated experiments, and it turns out that the experiments don't check what you think they're going to check. So it's always possible that there was a flaw with your experiment and you need to repeat the experiment. All right? So for instance, maybe you grabbed some batteries from your pile of spare batteries, but, maybe some of those batteries are dead. Maybe you got bad batteries. And you need to try to repeat that again. Get a different set of batteries and try it again. But let's say that you've tried it with a couple of different sets of batteries. You are convinced that these are good batteries, and you've got them plugged into your remote, and the remote is still not working. Now you need a new hypothesis. Maybe the problem isn't with the remote. Maybe the problem's with the TV. Have I checked to see if the TV is plugged in? All right. Prediction. The TV isn't plugged in. If I plug the TV in, the remote will work. Experiment. I go and check. TV's plugged in. All right, that hypothesis was wrong. What's next? What's another explanation, right? Maybe the little detector thingy on the TV is blocked, right? So my prediction is that if I go and find the little detector thingy on the TV, it will be, blocked, and if I move whatever's blocking it, then the TV will work. I go there and I find that, the little, there's a big metal can or something sitting right in front of where the little infrared detector thingy is on the TV, and I move the can, then I go back, click the remote, boom, TV turns on, right? Now I've finally got a hypothesis that has been supported, and if I wanted to, I could make other predictions, like, okay, I need to know what I can place in front of this thing and what I can't. Maybe I could try placing something clear, like a soda bottle, in front of it. Would that block it? Or I could just sit down and watch my TV, because I've solved my problem. Not everyone needs to take scientific theory to their ultimate conclusion. Sometimes you take your scientific experiment, you use it to solve your problem, and then you just get on with your life. That's what most of us do most of the time, and that's fine. It's totally valid to do things that way. So what is a theory? A theory is an often misused term. at least from a scientific perspective. One of the things you'll find is that in science, we sometimes use words that you use in not science, but they don't mean the same thing. So if you're watching, like, I don't know, CSI or, Law and Order or something like that, someone says, I got a theory about what's going on in this case. What they mean is they've got a guess. And in reality, in scientific terms, what they have is a hypothesis, right? They have a potential answer to a question that has not been tested yet. And it always annoys me when I see theory used like that. I know that it's fine, and, different usages of a word sometimes just work differently. But just like a guess or just a simple explanation that's been untested, in science, that's not what a theory is. Scientific theory is usually much broader in scope than a hypothesis, right? So a theory you wouldn't develop the theory of, worn out batteries. Usually a theory is going to address a question that applies to a whole field, and that could have many, many different instances of it. And usually a theory is developed only after many, many hypotheses have been developed and supported. And the theory explains why all of these similar hypotheses are all correct and accurate, and why they have all been supported. So it's not like you say, this is just a theory, and that means it's just a guess. It isn't necessarily true. Like, in science, theory is usually as high as it gets. There are also laws, but theories don't become laws. This is something that I was taught when I was in middle school or something, that you have a hypothesis which becomes a theory, which eventually becomes a law when it's tested enough. It's not the way it works. Theory is the highest you go. Nothing ever stops being a theory. Nothing ever is so well supported as a theory that it becomes a law. Theories and laws are different things, right? A law is just an observed phenomenon, right? So the law of gravity is that unsupported objects fall to the center of the Earth at 9.8 meters per second squared. It doesn't say anything about why. It's just, this is a thing which has been observed and measured. That's what a scientific law is. They're usually mathematical in nature, and they just say, this is a thing that has been repeatedly observed, and this is how it works. A theory is usually an explanation of why it works that way. So the theory of gravity, as developed by Einstein, is that the reason why unsupported objects fall towards the center of the Earth, it has to do with how mass warps space-time, and how mass interacts with the fabric of the universe around it, creating a divot in space-time that things fall into. And so the fact that Einstein developed the theory of gravity many, many, many years after Newton developed the law of gravitation should tell you that theories don't become laws. A theory is usually an explanation why, and a law is just an observation of. Theories, in theory, God, now I'm using the word wrong. So, you can call anything you want a theory, but for something to be an accepted theory within science, it has to be supported by an accumulation of many, many tests that that have been performed and have supported it. There are some things that end up being called theories, even though they have not been tested. Like if you watch a lot of like Nova or, Discovery Channel stuff, you'll eventually see somebody talk about like the theory of everything and string theory and stuff like that. And like these are theories about how the universe works that, as far as I know, cannot be and have not been tested. They are explanations. They're sometimes mathematically very beautiful explanations, but some of them like just simply can't be tested, at least not with our current understanding of, like, we don't have the technology to test them. And I would dispute that these things are not really scientifically accepted theories. The people who study them might disagree with me, especially if they're looking for grant funding. But I would say that in order to be a scientific theory, something must be testable. If it's not testable, then it's not really a theory in the scientific sense. And I want to point out that, scientific theories are not the only way we have of knowing things. But what it is it's an objective way of knowing things. Science, religion, art and philosophy, I should put in, are all different ways of trying to make sense of the world around us. And they're all valid. But they're not all equally applicable. So, scientific theories are very, very useful because they can tell us about the world in a way that is objectively measurable, where everyone can, agree that, yes, this experiment was done, the results have happened, the experiment has been repeated many, many times by many different people. Everyone can kind of agree that it's true. And you're always going to get some detractors, people who don't particularly care about things like that. But, there are flat earthers out there. But at this point, I think pretty much everyone admits that the earth is round. This is an observation that has been made many, many, many times. So we can all kind of agree on it. We can all have a starting point. With religion and art, these are intuitive ways of understanding the universe, but they're not necessarily ways where your understanding can be clearly demonstrated to somebody else. That's part, art doesn't mean the same thing to everyone. Two different people could look at an artwork and get two different impressions of it, and it could mean two different things to those people, and that's fine. Because art is not intended to be an objective expression of reality. It's a subjective expression of reality. But science and scientific theories are the objective way of knowing about reality. There are other ways that have a lot of facility for a lot of people, especially since there are a lot of things that science simply cannot tell you. Science can tell you about gravity. Science can tell you about pigmentation. Science can't tell you what is good. Science cannot tell you how to behave in a moral manner. Science can tell you if you, pull the trigger on that gun, it will expel a projectile that will almost certainly change this living creature that you are pointing it at into a dead creature. But science can't tell you when that's a moral thing to do, because morals are not objectively testable. Science can only tell you about things which are observable and things which are testable. So we need these other ways of understanding things, because science doesn't get you everywhere. In general, science is progressive, by which I mean it builds on previous information. Every scientist stands on the shoulders of every scientist that came before them. Generally speaking, in science, repeatability is considered to be very important. Just because you did an experiment that proves something, like, we don't just go with that and go, okay, that's solved then. Because you might be lying. You might have screwed something up. Maybe it only happens that one time. Maybe it only happens in New Jersey. And, like, if you test it anywhere else, it doesn't happen that way. Who knows? So in science, you usually, you have to repeat your experiment multiple times and get the same result for it to be taken seriously. And even then, other people have to be able to repeat your experiment in the same way you did it and get the same result that you did before we accept a theory. Or even before we accept the results of an experiment. So science is a community. It works really only if you have not just one scientist, but many scientists checking the conclusions of other people and attempting to repeat the experiment. In general, scientists are skeptics, and this term has gotten a lot of bad press. I think because there are a lot of people who misuse it and mischaracterize it. Right? So when we're talking about scientific skepticism, what we mean is that any assertion of fact needs to be supported by evidence. You need to be able to point to, I know that this is true because of this, this, and this. Some people on the internet use what I would call radical skepticism, and claim I'm being, I'm just a skeptic. But it isn't really scientific skepticism, because all scientific skepticism is based on a prior, you are asserting this, the common wisdom says this, I need you to prove your point if you want me to believe something new. And the commonly accepted scientific theory is usually something that's based off of a whole lot of evidence. It's been tested many, many times. And so if you are going to dispute that understanding, then you have to bring an equal weight of evidence to your argument. Now, some people just use the term skeptic by meaning that I'm choosing not to believe this thing, and instead I'm going to believe this other thing without any weighting of the evidence. Like you could say, I'm a vaccine skeptic. I don't believe in vaccines, and I'm skeptical, and skepticism is scientific, so you have to accept that. And that isn't the way it works. All right? So there is a lot of evidence for vaccines. It has been published many, many, many times. It has been repeated by many, many, many people, right? That is the currently accepted, vaccines work and are not necessarily 100% safe, but nothing is. And vaccines that are in the current public use are fairly safe. That's the general scientific understanding. Skepticism would say that since that is the currently very well-supported theory, you should be skeptical of anyone who comes in and says the opposite. Anyone who comes in and says, actually, vaccines don't work, or they aren't safe. That's what you should be skeptical of, because there is so much weight in support of the argument that they do work. So if you're going to come in and say vaccines don't work, You need to come in with an equal amount of evidence or a very convincing set of evidence. You can't just say, oh, well, I'm skeptical about it. Because you're not being skeptical about the opposite. You're saying, oh, I'm going to be skeptical that vaccines work, but I'm not going to be skeptical that they don't work. When one of those positions, the one that you're skeptical of, has a whole lot more evidence behind it than the one that you're taking. But scientific skepticism does mean that you have to be willing to accept that if somebody comes in with a whole lot of evidence that, in fact, this thing that is in the common wisdom is incorrect, you have to take their argument seriously. You have to be willing to actually examine the evidence that they bring to the table. And this has largely been done in the vaccine debate and the global warming debate and these things. Like people bring in, they say, I don't accept this theory. And we say, okay, well, what's your evidence? Bring it to the table. And then we compare the weight of the evidence. And generally, as a scientific community, we make decisions based off of the weight of that evidence. How much of it there is, how well it was collected, how repeatable it is. And there have been some scientific theories which have been refuted. I should point out that it's very seldom that it actually gets totally refuted. Usually what it will be is like some small aspect of it was wrong, or that what we believed was actually like a specific case. And there are a whole bunch of exceptions to it. So, for instance, we used to believe that all eukaryotic proteins were made through a loop mechanism. And I know that probably doesn't make any sense to you, right? But like, this is a thing that we used to believe about how DNA and RNA was turned into proteins, was that it in eukaryotes, it happened through like this loop that occurred on the ribosome. And then there was a whole lot of evidence brought in that actually, that isn't always true. It's usually true, like 99% of the time it's true, but that there are exceptions to that. And so we had to go back and revise it and say that, okay, this isn't what's always true. This isn't the only way it works. This is the normal way it works. Here are a few other options. And they work through these different mechanisms. And so the theory on how these proteins were made was broadened. That's the more normal way that things change. Very seldomly does someone come in and say, actually, all of this evidence that you've accumulated, it's all wrong. That used to happen sometimes. It almost never happens these days because we've gotten much better about how we, because the science has gotten better, basically, because we've gotten much better about how we understand data and interpret data. And because the scientific community has grown to the point where, like, any fraud usually gets found out very quickly. Long and short of that is that words like theory and skeptic and things like that sometimes mean something a little bit different when they're used in a scientific context than when they're just used in everyday speech. Science has a few features that I've mostly already mentioned that distinguish it from the other forms of inquiry. Science depends on observations and measurements that others can verify. Like, it isn't just how I feel about something. You can go do the same thing and you can get the same results, assuming you have the funding to do so. And science requires ideas that are testable and that others can repeat. Like, if I come up with a theory and I say, this is my theory for this, I go, okay, well, how are you going to test your theory? I would say, there's no possible way to test this. Well, then what I've developed is not a scientific theory. All right. So that is the scientific